Hi guys, today we are going to be moving on to chapter 5 and we're doing chapter 5 in about 4 sections. So you'll want to keep an open Google Doc, you want to title it chapter 5 notes, and at the very end of all of the notes you'll be turning that in. So that's not going to happen until after Thanksgiving break. So we'll be working on these notes for roughly 3 weeks, which I know sounds like a long time, but remember you have that big Thanksgiving break in there, so that takes up almost an entire week itself. So the first part of our notes is just about diffusion. So I'm going to start off with talking about the animal cell here, and we are looking at the cell membrane. That is the main portion that surrounds the entire animal cell. It keeps everything in its place where it should be, and it keeps things that are outside of the cell from getting into it. Most of your cells are made up of water. We went through water back in chapter 2, and we know that it's extremely important for all life, and we're going to be talking a lot about water again whenever we get to osmosis. So think of your cell kind of like a baseball or even like these Cheerios here. Water or milk is going to be rushing inside of the Cheerios or rushing inside of this baseball, and it gets really waterlogged, or your cereal is going to get really soggy. And that kind of happens to your cells as well. And whenever things get waterlogged or mushy, they don't quite taste the right way, and they don't function the right way either. We also have another thing that can happen to our cells. They can go through a plasmolysis, if you will, which means that they are shrinking up, and that also depends on how much water is coming into or going out of their cells.
Attention students, we will start pictures for the 11th graders. Students with the last names beginning A through E, you may report to the auditorium at this time.
Today's picture day, so I assume there will be a couple interruptions and we'll just roll with it. Here's a close-up picture here. This picture here shows you the section that I'm zooming in on. So that's what it looks like. Your cell membrane's on the outside, and you can see that it actually allows particles to be expelled from it. It kind of looks like a pimple when it gets popped, which coincidentally, this is actually what happens. Your pore is going to be opening up and all that goop is going to be coming out of it. I'm not going to worry about playing any videos for right now. Let's just get through the main points here. So the characteristics of the cell membrane. We know it is made up of phospholipids. We learned that back in chapter 3. They are composed of phosphate heads and fatty acid tails. It's also called the phospholipid bilayer. The prefix bi means two. Therefore, the phospholipid bilayer means that the cell membrane is made up of 2 layers of phospholipids. So that part in red is what you're going to be writing down today. Some people were having issues with seeing the color blue in comparison to black, and since my background is green, I figured the red might stand out a little bit better. So here's what the structure looks like. You have a phosphate head, which is hydrophilic, meaning that it loves water, and these fatty acid tails, they look like spaghetti noodles. They're hydrophobic, and they hate water. You can think of your cell membrane like a double-layer cake. So you have the phosphate head is the cake part, and right in here, that is the fatty acid tails. And those fatty acid tails are going to keep those 2 layers separate yet combined. If we're just looking at your cell membrane, this is what it looks like. Here's outside of the cell, and there is water on the outside. And there's also some water on the inside of the cell, which is why we have those hydrophilic phosphate heads both as the border. Now, the tails, we know they hate water, so this water on the inside or the outside, it cannot mix. It will stay completely separate, which allows the stuff that is inside of your cell, all those organelles that we just learned about, to stay in the cell instead of being kicked out of the cell. Again, anything in red is what you're writing down. So the phosphate groups are hydrophilic, and that means water-loving. If you don't know what hydrophilic means, you may want to write down that it's water-loving. This means that the outside of the cell membrane will be attracted to water. So we've talked about the little blue points, the little blue balls, that is the phosphate heads. The fatty acid tails are hydrophobic, which means that they are water-fearing, and this means that the inside of the cell membrane will not mix or be attracted to water. The inside of the cell membrane is those gray little spaghetti noodle stick-like things. There are two different types of transport. We have passive transport, which does not use energy to bring in materials, and active transport, which requires energy to bring in materials. We're going to talk about passive transport first, and we'll do that one prior to going on Thanksgiving break. When we come back, that's when we're going to talk about active transport, and that is when you'll finish up your notes. So starting off with passive transport, here are the three types. We have diffusion, osmosis, and facilitated diffusion. Now, diffusion by definition is the movement of molecules from an area of higher concentration to an area of lower concentration. Diffusion is going to move down a concentration gradient. Now, if you don't know what a concentration gradient is, that is the difference in concentration of molecules across a distance. Diffusion is going to require no energy because it is a form of passive transport. So let me give you an example of that. So I have a beaker of just regular plain water, and I'm adding food coloring to it. You can see at first the food coloring is very concentrated in one area. But on the outside, towards the glass, there is no food coloring. So those molecules are going to start to push each other apart. So they're going to diffuse into the glass until there's an even layer or an even concentration of purple molecules throughout the entire glass. Another example, looking at our cell membrane, so here's outside, here's inside, and all these little purple particles, those are solute molecules like sugar or salt. They are going to move from an area of high concentration to an area of low concentration. They want to get as much space around them as possible. They don't like to be compacted and stuck together, so they're going to move away from one another. If you use any kind of colognes or body sprays and you spray it, if I sprayed something in the front of the room, and you could even do this at your own house, spray it on one end of the room and wait and see how long it takes for the person on the other side of the room to smell it. That's a great example of diffusion right there, because as soon as you spray it, those particles are really concentrated in that area, and then they are going to spread out from one another. Diffusion will continue until equilibrium is reached, and an equilibrium is when the concentration of molecules is the same throughout the whole space that the molecules occupy. In diffusion, molecules are going to pass between the phospholipids in the cell membrane. So these molecules are small enough to be able to fit right through your cell membrane. So here's the high concentration. This is where it starts out at. Time is moving to the right. So we have a high concentration, and then they start to move through the membrane into the cell, and eventually we have an equal number inside as we do outside. Since the molecules pass right through the cell membrane, diffusion can only move small, nonpolar molecules. They have to be nonpolar molecules because those fatty acid tails are nonpolar, and they will not let any kind of a polar or ionic substance through them. That's why water can't get through, because water is polar. And we're going to stop right there for our first part. Remember, I told you we're doing this in 4 separate sections. So next time we do notes, we'll be looking at osmosis. All right, guys, have a good one.